This is an early print of a patent for a hot air engine submitted in 1816 by Robert Stirling, a Scottish minister. Today, with the help of modern materials and with new knowledge of flow and heat transfer phenomena, a highly efficient engine has been developed. But the fundamental principles of the Stirling cycle are unchanged. What then are these principles? At the heart of the engine are the cylinders. In each cylinder, a certain quantity of gas is retained by a piston. Assume that the gas pressure on either side of the piston equals 1 atmosphere. No force on the piston results. With the piston held in position, let the head of the cylinder be heated. Pressure of the gas rises. This force results. Now let the piston be released. It is driven by the expanding gas until the pressure to the left of the piston reverts to 1 atmosphere. If the cylinder head is cooled, the pressure of the gas decreases further. A force is now exerted on the piston in this direction, a force which drives the piston back to its original position. Let us relate this cycle to a PV diagram. We start with this given volume and a pressure of 1 atmosphere. When heat is supplied to the cylinder, the pressure rises. This distance is proportional to the force acting on the piston. When the gas expands, its pressure drops. The force becomes smaller. This area is proportional to the energy delivered by the gas. During cooling, the pressure of the gas in the head becomes lower than 1 atmosphere. The piston driven now to the left delivers yet more energy. The work done in one cycle is proportional to the area enclosed by the related curves. This cycle turns heat into mechanical energy. But the power of the simple device considered so far is small, and its efficiency low. The power can be increased by raising the pressure on both sides of the piston to a larger value. In the modern Stirling engine, this may be 100 atmospheres. The forces induced by heating and cooling will increase correspondingly. So will the energy delivered per cycle. To show this on the PV diagram, the pressure scale has to be condensed. Now the cycle starts with a pressure of 100 atmospheres. The area indicating the energy per cycle has increased so much that at the same scale the original area can hardly be seen. So far it has been assumed that the pressure to the right of the piston remains constant throughout the cycle. This doesn't apply in practice. The volume to the right of the piston obviously changes. So does the pressure. However, the pressure is kept reasonably constant by including a cavity known as the buffer space. The power of the cycle has been raised. Now let's turn to the efficiency. As well as the gas, the cylinder wall is alternately heated and cooled. The heat so expanded is wasted, but it can't be neglected as the heat capacity of the cylinder wall is much higher than that of the gas. The genius of Robert Stirling solved the problem with the so-called displacer piston. This piston can drive the gas from one end of the cylinder to the other, hardly demanding energy. This is because the pressures on either side of the piston are almost equal. The cylinder head can now be kept constantly at a high temperature and the other end at a low temperature. The whole cycle can be performed without wasting heat energy on the cylinder wall. First, the gas is displaced to the cylinder head, where it is heated. Then the gas is expanded, and work is done on the power piston. The gas is driven to the right and therefore cooled. Then compressed, and again work is done. But even here, heat is being wasted. It's being wasted on the gas itself. A certain amount of heat is being supplied to the gas, and yet, a half cycle later, it's being removed again and lost. The engine's efficiency could be increased if only this heat could be conserved somewhere to be used later in the cycle. Stirling again provided the basic solution. We call it a regenerator, a chamber filled with a porous metal which acts like a sponge. To this chamber the gas gives up heat during one half of its cycle, only to take heat back on its return. With this modern version, more than 99% of the heat, otherwise lost, is recovered. There is now only one essential reason left to supply heat to the cylinder head, which is to compensate for the tendency of the gas to cool during expansion. Conversely, there's also one reason to remove heat from the other end, which is to compensate for the tendency of the gas to heat up when compressed. But now, too, the amounts of heat to be supplied and removed are much smaller than before. The efficiency as well as the power of the original Stirling cycle are increased still further by raising the expansion temperature and by using hydrogen or helium as a working gas instead of air. The movement of the displacer piston is regulated by the power piston through the so-called rhombic drive. These are the four phases of the cycle. First, the gas is driven to the hot space, where it is expanded, driven back to the cold space, and ultimately compressed. With the use of the rhombic drive, the four phases of the PV diagram will partly overlap, resulting in this shape. The work done is still proportional to the area enclosed. This is how the rhombic drive is built up. The mechanism comprises two pairs of connecting rods of equal length. One pair is connected with the yoke of the power piston, and the other pair with the yoke of the displacer piston. The yokes are of equal length as well. Due to the symmetrical buildup of the drive, there are no resulting inertia forces in the horizontal direction. Furthermore, the vertical inertia forces acting in the mechanism will not be affected by the assumption that the masses of the pistons are concentrated in their respective yokes. If these masses are equal, then the center of gravity of this rhombus will coincide with the geometrical center. The center of gravity is displaced vertically. The inertia forces which result can be compensated by two counterweights, whose combined center of gravity is in counter movement to the center of gravity of the rhombus. The masses of these counterweights can be evaluated so that the center of gravity of the whole system remains static. This means that this single-cylinder hot gas engine is inherently balanced. With this balance, it is possible to run the engine at high speed. This leads to high power. With both high speed and high power, the modern Stirling engine needs an improved heat transfer system. This can be achieved by placing more heat exchange units in parallel. Efficient cooling is ensured by subdividing every cooler tube into many smaller ones. All these are embedded in the cooler housing through which water is pumped. The heater is improved by extending the heater tubes, increasing their number, and adding fins. The exact dimensions of the heat transfer system result from a thorough investigation of the Stirling cycle and have been evaluated electronically to minimize the sum of all the losses. In section, it can be seen how a burner is placed inside the heater. The actual combustor is suitable for a wide range of gaseous and liquid fuels, which are fed in at the top. The fuel and air associate to become the hot combustion gases which circulate around the heater tubes. The efficiency is increased by using a preheater. In this, the air is led to the burner against the flow of the combustion gases, absorbing heat from them and thus reducing chimney losses. The heating system, being external, is very flexible indeed and can be adapted to use nuclear or solar energy. This is the end result, a powerful, quietly running engine with a high efficiency, nearly 40%. It has turbine properties inasmuch as it can be completely balanced, and for a model with only 4 cylinders, an extremely steady torque is obtained. The Stirling cycle is very versatile. It can also be used as a refrigerator. In this case, there is no need for a heater, and the shape of the head is changed. The direction of rotation remains the same. The machine is driven by an electric motor in what we will call the forward direction. Again, expansion takes place in the head of the cylinder, compression at the base. In the expansion space, the gas will cool. In the compression space, heat does develop, but only to be removed by cooling water. Thus, heat is transferred from the head to the cooling water. It's even possible to cool the head so much that the surrounding air is liquefied upon it. The Stirling cycle, then, can be used as the basis for a hot gas engine or a refrigerator, the machine running in the same forward direction in both cases. But if the direction of rotation is reversed, 2 other ways of operation are obtained. When the electric motor is switched on to drive in the forward direction, the machine will act as a refrigerator. The water vapor from the air condenses on the head, and a thin layer of frost is formed upon it. At a later stage, the head becomes so cold that the air itself is liquefied. The rate at which the air is liquefied is best seen by collecting it in a ring. Cold that is stored in the head may be used to obtain mechanical energy. When the electric motor is switched off, the machine itself will start to run, but in the reverse direction. It acts now as a cold gas engine, as long as the head remains cold enough. Before the cold gas engine comes to a stop, the electric motor is switched on again to keep the machine running in the reverse direction. Therefore, the head will continue to be heated up, and the machine now operates as a heat pump. We will now extinguish the lights. The glowing head indicates that a temperature of about 700 degrees centigrade has been reached. This heat is turned into mechanical energy by switching off the electric motor. The machine now runs in the forward direction as a hot gas engine. An experimental Stirling engine has been installed in this floating laboratory. The purpose was to test the behavior of the engine and its auxiliaries in practice. The engine has a rating of 30 horsepower at 1,500 revolutions per minute. The working gas is helium. The boat has been provided with an inboard-outboard drive. Let's look at the engine. The large cylinder is the preheater fitted around the head of the engine. The fuel atomizer is seen at the top. The power output of the engine is proportional to the mean working pressure. If the governor is set to a higher speed, helium from a high-pressure bottle is blown into the cylinder, quickly increasing the working pressure and the power. The pressure also controls this variomatic drive of the blower that supplies the air required by the burner and keeps the air-fuel ratio constant. On the other hand, by lowering the set speed, a dump valve is opened and a compressor pumps helium back to the pressure bottle. Moreover, a short-circuit valve is opened, which makes a connection between the buffer space and the cylinder, thus momentarily cutting the power and giving excellent maneuverability to the boat.